acids and bases. So pH is the power of hydrogen. So that's the negative log of the hydrogen ion concentration in the solution. So something with a low pH is acidic, something with a high pH is basic or alkali. So strong bases will be on the right side. Here with strong base with pH of 14. Neutral things have a pH of 7, like pure water, and acids have a low pH. The continuum goes from 0 to 14. Acids. They're substances that donate or break down into hydrogen ions in water. So sulfuric acid, nitric acid, hydrochloric acid, phosphoric acid, anything that ends in acid is typically an acid, and these donate hydrogen ions in water. And they're very corrosive if you get them on your hands, and if they're strong enough, they will eat through your hands and anything that they land on. So be very careful. Acids have a sour taste. They turn blue and red, and react with some metals to produce hydrogen as a gas, and they dissolve carbonate salts to release carbon dioxide. Bases are substances that donate or break down into hydroxide ions in water. So anything from groups 1 or 2 that end in hydroxide, so like barium hydroxide, calcium hydroxide, lithium hydroxide, etc., will be bases. So it'll be a OH2 or LiOH. Those are all bases. They have a bitter taste, and they turn red litmus blue, and they're slippery to the touch. So they include things like soap and a lot of cleaners. Neutral means having equal concentrations of hydrogen and hydroxide ions. Neutral solutions have a pH of 7. As you can see, if you combine the H plus and the OH, you get HOH, hydrogen hydroxide, or H2O, water. So pure water, salt water, sugar water, these all have a pH of 7. They don't have acidic or basic properties. They are neutral. Bronsted-Lowry acids and bases. So these are, by this definition by Bronsted-Lowry, two scientists, acids are proton donors and bases are proton acceptors. So here in the examples, we see that this HA, the general acid, plus water that can act as both an acid and a base, is going to become H3O plus because the water acted as a proton acceptor. It accepted that hydrogen proton, became H3O plus, and now this A is just left as A minus. We call that a conjugate base. Something that was an acid, and after it gave up a hydrogen, it becomes a conjugate base. And here we have a base A minus will accept a proton from H2O to become HA, conjugate acid, and leaving hydroxide as this OH minus from water. Lewis acids and bases. So these acids accept electron pairs. Lewis bases donate electron pairs. So here we have NH3, and it has this electron pair that's not shared. So it can donate that pair to this hydrogen. So this accepts that electron pair, so we get NH4 plus. So here we have the Lewis acid that accepts the electron pair, is that H plus, and Lewis base is the NH3, the ammonia molecule. When we have a titration, that means whether we're adding an acid to a base or a base to an acid to change the pH of the solution to 7 and neutralize it. So if we have something that is acidic, we can add a base to make it neutral, or if we have something basic, we can add acid to make it neutral. But you have to add the exact amount. So here's an equivalence curve for a titration curve. So this is the equivalent point here. This is at the point where we've added just enough sodium hydroxide to HCl, hydrochloric acid, to reach the equivalence point where the pH is perfectly 7. Now, if we add 1 drop above that, the pH shoots up to whatever the base is. So it's very, very difficult sometimes to find the equivalence point. A buffer is a chemical that helps keep pH from changing. So if you add a buffer, then the solution will resist changes in pH. Example is Tums or any other antacids that you might see. Now they operate by, if you have too much acid in your stomach, getting acid reflux or something like that, then you take the antacid and it will help neutralize the acid and make your stomach resistant to changes in pH.